Good morning and welcome back to Chapter 4. In this section, we are going to start looking at the graphs of these trig functions. This first one is sine and cosine, which are called sinusoidal graphs. The next section will look at the other four trig functions. So, our learning targets for today, we're going to be able to find the amplitude period and or frequency of a transformed sine or cosine function or graph. Also be able to define those words. We'll be able to graph the sinusoids, identify maximums, minimums, and zeros, describe transformations necessary to obtain graphs from basic trig graphs, and then construct a sinusoid with given amplitude and period that goes through the given point. So, the very first thing is we're going to look at the graph of a sine function. So the sine function, if we think back to our unit circle, we're going to plot some points. We know that it's 0 a few different times. We know that it's 0 at 0. And let's see, I have it 2 pi, I have a 4 pi, 4 pi. We know it's 0 at the negatives as well. It's also 0 at pi's. Now, notice that my graph, the axes are not the same, like the x-axis and the y-axis are not the same. The x-axis I have measured in pi's, and the y-axis is just numbers. But notice, like, so we go over 2 pi when we go over 4. 2 pi is like 6 point something. It's like 6.28-ish. So even though we're only going over the same amount we're going up for 1, it's not scaled the same. So this would be way stretched out. Now, if I did that, it would just be really hard to kind of see what it is that we're doing. But you'll see a lot of times that the trig graphs will be much more spread out than that, or than what we're going to see here. So anyway, so we have zeros at those points. That means that the middle points are the pi over 2's. Pi over 2 is when sine equals 1. Wow, this is going to be really steep. So it's going to equal 1, it's going to equal -1, and then we get another rotation of it. And we could go backwards. So I'm just filling in those cardinal values from the unit circle. The horizontal and vertical asymptotes. So now we have this, and it looks all sorts of jumbled. We're going to connect the dots. Now, right where I have it like this, it looks like if we connect the dots, we're going to get a bunch of zigzags. Which, yes, you could actually connect the dots with a bunch of zigzags, but that's not going to be what the sine function looks like, because the sine, it's going around a circle, and so it's not going to have those sharp corners. It's going to be rounded. So, and this is much easier when it's spread out a little bit more, and we'll see we'll see a few better graphs of this. But it goes and it's rounded, and I do understand that sometimes graphing these can be a bit of an art form, but try to keep the points rounded more than pointed. This one right here looked more pointed than rounded, but it looks kind of like that. So that's the graph of the sine function. We've actually seen this before. Way back in chapter 1, we looked at a whole bunch of basic functions, and we just briefly touched on the sine function. And so this is more what it usually looks like as the axes are closer to even. And so we have the sine to domain. It goes from -infinity to infinity because we can keep going around the circle. The domain is that angle. It's that center angle. So we can call it x, we could call it theta, we could sometimes call it t, but the domain could be everything. The range goes from -1 to 1, because remember, as it's going around that unit circle, the biggest thing it's going to get to is 1 at the top of the circle, and then it goes back to 0, and then it goes down to -1 at the bottom of the circle, and back to 0, and then it just repeats it. So it's continuous. There are no gaps because the angles, it just keeps working. Um, it's neither increasing nor decreasing. It alternates between that. It's a wave. Sometimes we hear about sine waves. And in fact, sine and we'll see cosines are similar. Those functions are used to model waves or anything that has that oscillating thing like a spring bouncing up and down. We use sine or cosine to model that. It's symmetric with respect to the origin, which means it's odd, which means that if you turned it upside down, like if you actually took your device and you flipped it upside down, well, the screen rotator would probably rotate it right back to where it was. But if it didn't, it would look the same. So if you had it on a piece of paper and you flipped it upside down, it would look exactly the same. It's bounded, which just means that it doesn't go above that 1 or below the -1. It doesn't go off to infinity in the y direction. It has absolute maximum 1, absolute minimum -1. There's no horizontal asymptotes or vertical asymptotes. And the end behavior doesn't actually exist because it keeps going back and forth between 1 and -1. So it doesn't go to a specific value or off to infinity like all of our other functions have. They have all either gone to infinity or to a specific value. Um, and so that's what the graph of sine looks like. Now the graph of cosine is going to be similar. The difference really is that at 0, it starts at 1, and then it'll be 1 at 2 pi, 1 at 4 pi, because that would be those same angles, right? Those are coterminal angles. Every 2 pi is a coterminal angle. Notice I'm doing this in radians and not degrees as well. Generally speaking, when we're looking at graphing trig functions, it's in radians. The -1 is going to be at the odd pi's, so at 1 pi, at 3 pi, -1 pi, -3 pi, and then at the pi over 2's, it's going to equal 0. And then we can, once again, connect the dots using nice, smooth curves, not zigzag. Right? And so this looks very similar to sine. We're actually going to see them graphed next to each other, like with a real graph, not with one that I draw, so that we can see what they look like. So the cosine function is almost identical to the sine function in all of these. The domain, negative infinity to infinity, range is -1 to 1. It's continuous. It's going in waves, just like sine. It's bounded between -1 and 1. No asymptotes and no end behavior, just like the sine. And we're going to see on this next slide why those two are so similar. So if we look at these, the blue one is the sine and the red one is the cosine. See how similar they look? So this would be pi over 2. So if we took the sine function and shifted it that way, pi over 2, we get the cosine function. So a horizontal shift, sine of x, then we have to go left, so plus pi over 2 equals cosine of x. Or we could go the other way. Cosine of x minus, because we have to go to the right, pi over 2 equals sine of x. So we can go back and forth between them. They're just a horizontal translation of each other. And sometimes that's something that we do. But what's cool about that is that means that if we just look at rules for one of them, as far as graphing, that means that we get the rules are the same for both of them. So speaking of rules, so these are called sinusoids, these two functions. The other trig functions are not really. These two behave the same. The others four don't. The other four look very, very different. We'll see that next time. But these two are called sinusoids. And what we can see with sinusoids, or so the definition, it's a function that can be written as f of x equals a times sine of bx plus c plus d. How nice is it we have a, b, c, d instead of like h and k and all those kinds of things. And so in this, neither a nor b could be 0, but c or d could be 0. So let's look at these values like we have in the past, because we know what these things are. A, we're adding something to the end. The d, this can be a vertical translation. We're adding something to the x. The c is going to be a horizontal translation, which actually has a different name in sinusoids. It's called a phase shift. The horizontal translation, phase shift are the same. Why does it have a different name? I don't know. Possibly because if we shifted it like enough, we would actually end up with the exact same function because of the repetitiveness of the function. So it's a horizontal translation or a phase shift. And we'll see this a little bit more in just a minute. The number multiplied to the outside, the a, that's a vertical stretch, or also reflection if it was negative. And the number on the inside is going to be a horizontal stretch and reflection. So now again, these things do have a little bit more, a few different types of names and stuff like that, which we're going to be looking at here. So the A is the amplitude. Now the amplitude is a vertical stretch. Originally, the amplitude of the sine and cosine is 1. So when we put another number in front of it, it'll make it whatever that number is. So if we have 2 sine x, the amplitude is 2. If we have negative 2 sine x, the amplitude is still 2. If you notice here, it's the absolute value of a. And then graphically, it's half the height of the wave. So if we see the wave is going from 3 to 7, that means it's going up 4. So from the low point to the high point is 4. That means the amplitude is 2 because we're looking at the center line up. The period is kind of like the stretch or compression. That's how long does it take for a full cycle to get from the maximum point to the maximum point. And that involves B. Originally, the period is going to be 2 pi because that's one trip around the circle, and then everything repeats itself. So we have 2 pi divided by absolute value of b. Now, b is generally positive. We don't usually see a negative b, but sometimes we do. So it is important that that is positive. So the period is 2 pi divided by absolute value of b. And that's going to be how long for the full cycle. Again, to get from a maximum to maximum, minimum to minimum, or to get from the center, like a 0, to a 0, but we usually have to skip a 0 in the middle because that's only half the cycle. We'll see that in a second. The frequency of a sinusoid. Now, the frequency is how many cycles happen in one increment of time, or it's usually time. And so that's actually just the reciprocal of the period. If the period was p, the frequency will be 1 over p. So we actually use these in radio waves. Radio waves are used or we can use sinusoids to model radio waves. And there's a couple different ways that we can that we can measure radio waves. We can measure radio waves by the amplitude, or we can modulate them by the amplitude. So amplitude modulated, which is AM, or we can measure them or modulate them by the frequency. So frequency modulated, which is FM. If you look at your old AM FM radio, it actually gives you the units there. And so you can see the units between AM and FM are different because the AM, it's measuring the amplitude of the waves, and FM is measuring the frequency of the waves. So it's like hertz per second, or maybe hertz is something per second. But regardless, uh, and so the period and the frequency are basically the same. I mean, they're reciprocals, but they both use that B number. And it's always 2 pi over B for sine and cosine, because 2 pi was the original period. And then the phase shift. The phase shift is the plus C. But, and I've seen this in a book before, and I really liked it. So instead of writing it like they have it, A times sine of B times x plus C over B. Because when we do that horizontal stretch or compression, that's going to it's going to stretch the entire x-axis, which includes any kind of shift that we have done. And so having that factored out, this is a phase shift. It's plus, so it's going to go to the left. So it's negative C over B on the x-axis. It's that phase shift of that. So having that factored out, now a lot of times we have one or the other in here, but it is possible to have both. And so again, if you factor that out, that value, it actually does work out a bit easier. So let's take a look at one. First one, we're going to look at the graph and make an equation, and then we'll have an equation, we'll graph it. So first thing I look for is, where's that center line? This center line is at 1. That's that vertical translation, because the center line usually is at 0. Now it's at 1, so we know that D has to equal 1 because we've gone up 1. We can look at the amplitude. The amplitude is going to be this distance, which is going from 1 to 2's up here, so it's halfway in between. So the amplitude is 1/2. We can look at the period. So for the period, we can go from the high point to the high point. It's a little bit tough to see. We can go from here, take the full thing to here. So the period is 4 pi. So we have 4 pi equals the period, which is 2 pi over B. We need to figure out what B is. So we can multiply the B over, divide the 4 pi. And so B equals 1/2. Now C, like if this is a sine wave, we're starting at that center line. So we don't have a C for this one if it's sine. We could make it cosine and have a C, but really there's no reason to do that unless it's telling us to use cosine. So we're going to go f of x equals, we have the A, so 1/2 times sine of B, 1/2 x plus 0 plus 1. So that would be the equation, and we got that just from the different pieces, looking at the graph, looking at it to get each piece very specifically. All right, how about if we want to graph one? We can graph f of x equals 2 sine of 2x minus pi minus 2. So the very first thing I would do is let's factor out that 2. So we have f of x equals 2 then we have sine of 2x minus pi over 2 minus 2. So we're going to have a phase shift of pi over 2 to the right, because remember that horizontal translation goes over. We have an amplitude of 2. We have the d value, we're starting out at -2. The period is going to be 2 pi divided by 2, which is pi. So we can get a graph. Notice this isn't the same exact graph. I've adjusted it so that our graph would fit. It's kind of important. When we start, first thing, I would start with that center line, because this is what we're going from. And so the amplitude is 2, so we're going to be going up to there and down to there, up to the axis, down to -4. We're going to start out at pi over 2, shifted over. So pi over 2 is going to be right here. And the period is going to be pi. So that means after pi, so pi is going to be 4 boxes here. So that's going to be 1 full sine rotation. Well, what happens in the middle of the sine rotation? We have another 0. And then what happens to get to the 0? We go up to 1, then we go to 0, then we go down to -1, then we go to 0. And we can follow this. Like, notice I did not plug in a whole lot of values. I know the period. I know what happens halfway in the middle of the period. I know it's going to happen halfway in between those things. It's going to either be at 0 or 1 or -1. Now, granted, yes, this is going to be at -2 or 0 or -4, but it's the pattern that matters. And then we could keep going. So we had there, the next one's going to be up here, then we're going to be back here. We can go backwards, we're going to be here, there, up here, there, down here, up here, there, down here, there, and then connect the dots using that smooth sinusoidal. And so that's how you can graph it. Again, I start with the center line, and I know the amplitude, find the period, and then go from there, just using the same pattern that I know is going to happen with sine and cosine. So this is just a summary of all the different little things that we saw on the last page that were each in their own little thing. So this is all of them together. Modeling. So we can use these to graph real world situations and then answer questions based off of those. So ours, we have on a certain 4th of July in Galveston, Texas, high tide occurred at 9:36 a.m. At that time, the water at the end of the 61st Street Pier was 2.7 meters deep. Low tide occurred at 3:48 p.m., at which time the water was only 2.1 meters deep. Assume the depth of the water is a sinusoidal function of time with a period of half a lunar day, which is about 12 hours and 24 minutes. So the very first thing is, let's change this into hours. So 24 minutes is 0.4 of an hour. So that'll be 12.4 hours is the period. With that, we could find B, because we know that the period is going to equal 2 pi over B, which means that B is going to equal 2 pi over 12.4. which could be pi over 6.2, or we can make a a decimal for that if we really needed to. It's going to be about 1/2, right? Because pi is 3.1-ish, so it's going to be really close to 1/2. We have amplitude that we can find. We know the high point is 2.7, the low point is 2.1, so the amplitude is going to be halfway in between that. 2.7 minus 2.1. Well, not halfway in between, but it's going to be the half of the difference. So 2.7 minus 2.1 is 0.6, divided by 2 is 0.3. From that, we can actually find D as well, because D is going to be the point that's halfway in between them. Halfway in between 2.1 and 2.7 is 2.4, which we could get by 2.1 plus 0.3, or we could just add them together and divide by 2 to find that average. And then the phase shift, so we need it to be at the center time. So the center time is going to be halfway in between the low point and the high point. So we have 936 and 348. 936 is 9.6, so it's 9.6 a.m. Come on, right pen. There we go. And 3:48 p.m. So 48 is going to be a 0.8. 3 is going to be the 15th hour. So we have 15.8. If we find the average of these two, that's going to be the middle point between them. So we can add them together and divide by 2. At 12.7, which, what is 0.7? 0.7 would be 42 minutes, so it's at 12:42, which we could take it back a period, right? So it's 12:42 p.m. If the period is only 12 hours and 24 minutes, we could subtract the 12 hours and 24 minutes to get 18. So it's at 0:18, so midnight and 18 minutes p.m. a.m. because 0 is a.m. That's going to be the first center point. So not a high tide or low tide, but like the equinox of the tides. And then if we wanted to change the 18 minutes into a decimal, because equations don't like time, like minutes and hours, this is going to be 0.3. So that is going to be the phase shift is 0.3. So if we go to our equation, remember the equation, we can have the, we'll go the height of the water to time is going to be A times sine of B times X minus C plus D. I know I made it minus just because we're used to having that be a negative. Otherwise, we have to change the sign of the C. It comes out to be the same, but still. We can just plug everything in. H of t will be A. A was 0.3 times sine of B was pi over 6.2, I'm going to just call that 1/2, times x minus 0.3 plus d, which was 2.4. There is our equation. So now we could have, at what time on the 4th of July did the first low tide occur? Well, we could do that without finding the equation, because we know that the second low tide happened at 3:48. And so we can go, so for part A, we can go 1548 minus the 1224 to give us 3:18 a.m. Now, notice I changed it to 15. That just helps with the time. What was the approximate depth of the water at 6 a.m. and at 3 p.m. that day? So B, we just have to plug this in now. H of 6 will equal something. And at this point, I mean, you're just going to plug it into your calculator. This is not something that you're going to, have like one of the unit circle values you're going to just know. So we're just going to plug in 6. So we're going to have 0.3 times sine, making sure I'm in radians. 5, so 6 minus 0.3. And I recommend doing it bits and pieces. Like do the 6 minus 0.3 times 1/2, do the sine of that, then times the 0.3, and then plus 2.4. When you try to plug it all in all together, the chances of missing a parenthesis somewhere is huge. And then all of a sudden you get the 2.4 added into the inside and stuff goes wrong. Don't be afraid to do it step by step. But when you do this, you should get about 2.486 meters, which 3 o'clock is pretty close to low tide, which was, 6 a.m. was kind of in the middle of the two. So it should be about the middle point, which was 2.4, which is pretty close. And then at 3 p.m., you can't plug in 3. That's the 15th hour. So we're going to do the same thing, only we're going to plug in 15. And at 3 o'clock, it was close to low tide, so this should be close to low tide occurred at 3:45. Should be, but I'm getting, it's almost high tide. Oh, because we started out there, then we went to high tide. That's a negative. That's a rookie mistake. I apologize for that. So this one, it's a negative 0.3. So, if you don't learn from your mistakes, you have to stop making them. What do we learn from this one? Make sure you check to make sense. Notice as I was finding this value and it was like 2.6, I'm like, well, that should be close to low tide, but that value is closer to a high tide value. Now when it's negative, we get 2.137, which is way closer to low tide. Now if we go back in and we do that first one, so the part A didn't matter, but this one is going to be close to that. It's 2.313, 2.314 meters for that one, because we start at, I should have looked at part A, because if we're starting at just after midnight, we're going to go down to low tide. The graph of this one is going to look like this. So it's that negative sign. We have that reflection there. So even though the amplitude is 0.3, in the equation it's going to be a negative 0.3. And then what's the first time on July 4th when the water was 2.4 meters deep? For this one, we can solve it algebraically, but you guys don't know how quite yet. We get to that later on in the chapter. So how do you do that? You graph it. You plug it into the graph. Negative 0.3 times sine of 0.5 x minus 0.3 plus 2.4. And we graph it. And we probably have to adjust the window. X can go from 0 to 24, get a full day there. Y can go 0 to 3. And we want when it's 2.4 meters deep. Oh, well, that's the center point, right? Because 2.4 is the center point. We already found that. It was 0.3. But you could still find that using the graph. You'd graph 2.4 and you find the intersection point. I was just expecting it to be a number that's not the center line. But we already found that, so part C was at 12, then it was 18 a.m. because we don't have 0:18 because why not? So that is graphing sines and cosines. There's a lot of stuff there. We're going to build on that to do the other 4, but these 2 are definitely the basis of all 6 of them. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.